So let's start with problem number 1, which talks about the countability of various different types of sets. So we'll walk through each of the parts A through J one at a time, exactly define what the set is, and then conclude whether it is countable or uncountable. So 1a asks us about the set of natural numbers, and by definition, we say that the set of natural numbers are what we define to be countable. In particular, whenever we want to talk about countability, we make a bijection between the set we're interested in and the natural numbers, and we say if you have as many or fewer numbers than the naturals, then you are a countable set. All right, so now let's look at 1b, which talks about the integers. Now the integers, one would intuitively think, are in some sense double the number of naturals that you have, but as it turns out, this is also a countable set. Now, if we claim this, we have to show a bijection between the naturals and the integers. And the bijection goes from n to z. So what we really have to do is we have to take a list of numbers and map them onto the integers. The way we're going to do this is we're going to say, OK, well, I'm going to take 1 and send it to 1. And then I'm going to take 2 and send it to -1. And then I'm going to take 3 and send it to 2. And then I'm going to take 4 and send it to -2. And so on. I'm going to send the number 2k minus 1 to k and 2k to negative k. Now you can see that on the left side, all of these guys are natural numbers for me. All of these guys are the integers. So what am I really doing? What I'm saying is I'm going to map the numbers 1, 3, 5, 7, and so on onto 1, 2, 3, 4, and so on. And then I'm going to map, so these guys go here, and then I'm going to map 2, 4, 6, 8, and so on onto -1, -2, -3, and so on. And we can verify that this particular function is in fact a bijection. And once we do this, we conclude that the cardinality of the integers is exactly that of the natural numbers. So let me clear my screen. OK, so we conclude that the cardinality of the integers is exactly equal to the cardinality of the natural numbers. We can also conclude similarly that the set of all odd naturals has just as many elements as the naturals, like we just did, and similarly for all even naturals as well. So this set also has exactly the same number of elements as the set of natural numbers. OK, so that was 1b. Now let's talk about 1c, which talks about the set of rationals. Now we've seen this proof in lecture. And fundamentally, of course, the proof concludes that the set of rationals is equal to the set of naturals in its count. But let's take a minute to think about the intuition. While we were talking about the integers, there was this concept of a next integer, right? We made a pattern where we said 1, then -1, then 2, then -2. So when we were talking about the integers, what we did is we went 1, and then -1, and then 2, and then -2, and then 3, and then -3, and so on. But then if I'm talking about the rationals, right, let's take a minute and think if a and b are two rational numbers, then in particular, a plus b over 2, which comes right in their middle, is also a rational number. And so there is no concept then very intuitively of a next rational number, right? And then it's a little hard to think as to how can I list them out if I don't have a next rational number. And the fundamental idea behind this proof is we say, look, let me pick a rational number. Let me call it, so let me pick some x which is rational. Now by definition, x must be of the form p over q, where p and q themselves, so this guy is an integer, and this guy is also an integer, right? And then what we start saying is, let me list out all the integers in the world in one axis, and again on another axis. right? So I'll just say x belongs to q here, sorry. And now what I notice is every point on this plane, which is at an intersection of two integers, signifies some sort of rational number. So really then, all I have to do is mark all points on this plane. And then, in a very nice fashion, if I proceed this way, right, and I list everything first on this line, and then on this, and then on this, and here, and so on, I have in some sense made this concept of a next rational number, right? So let's say this was the point 2, 1, then this would represent the rational number 1/2. Okay, why is this? Well, so even before that, so you might ask, okay, well, let's look at all the guys on this line or on this line, right? They're either duplicates because they're all 0, or on the other line, they're all undefined because you're dividing by 0. Now that's okay because I can throw those numbers out. So when I make my listing, I say this is the first element, and this is the second, and this is the third and fourth. And now I have the same guy again because it's 0, so I'll throw it out. And then fifth. And now I have division by 0, so I won't count it. So this is next, and then this is next, and then this is next, and so on. And I can keep doing this again and again. So you can see that if I proceed along this spiral in this fashion, what I've really done is I've made a listing of every rational number in the world. So at this point, ask yourself, okay, can I guarantee that every rational will come somewhere in this listing? And the answer is yes, because every rational of the form P or Q, P over Q, will come when you hit P along this axis and Q along this axis. And then you conclude that the cardinality of the rationals is the same as that of the naturals, and we know that then it's countable. Okay. All right. So now let's talk about the set of all real numbers. In lecture, we've seen what's called Cantor's diagonalization, and we'll see a similar kind of proof in 1G. So let's just leave this off and say this is an uncountable set. And you show that it's uncountable through a diagonalization argument. Okay, so let's move on to E. And E says, okay, the integers which 8 divides, right? I'm sorry. So let's move on to E. And E says the integers which divide 8. Okay, well, what are the numbers which divide 8? Of course, 8 and -8, 4 and -4, 2 and -2, and 1 and -1. This is in fact a discrete set. So what we're trying to drive home here is this set of numbers, which looks like -8, -4. Because it's discrete, you can count it, because how many elements does it have? It's 1, 2, 3, 4, 5, 6, 7, and 8. So the cardinality of this set is 8. And then this is a countable set. In particular, it is also finite. So there are no problems at all. Okay? Now let's talk about F, which is all the integers which 8 divides. So now this says all integers of the form 8k, where k belongs to the integers, right? And now you can see that this, in fact, is an infinite set because you can keep going, such as 8, 16, 24, 32, and so on, right? Okay. But I claim that, in fact, this is a countable set. Now, there are two ways to observe this. One is to say, look, these numbers are themselves integers. So then any number which 8 divides is a subset of the integers, right? So if I define, so let me define S to be the set of all 8k such that k is an integer. At this point, you see that S is a proper subset of the integers. And then it means that the number of elements there must be less than or equal to the number of elements in the integers. And since these guys are countable, then of course this must be countable. So that's one way to see it. The other way is to set up an explicit bijection between S, so between, let's say, so that's one way to see this intuition. The other way is to set up an explicit bijection between Z and S, and I name this bijection as f of x goes to 8x. And you can verify that, in fact, this is a bijection, and then it follows that the cardinality of S is the same as the cardinality of the integers. And this is countable, so then this is also countable. Okay, so that was F. Now let's talk about G. G talks about functions from n to n. But let me just talk about first one function from n to n. This is a function, let's call it f1, which takes in its input a natural number and outputs a natural number. So one way to define f is through some complicated function where I say f of x is 3 times x plus 4 minus 1 and so on, right? The other way to list f is to do some sort of a proof by cases kind of analogy where I say, look, I don't know the formula, but I know f of 0 is this number, let's call it 0. F of 1 is, say, 1. F of 2 is some 4. F of 3 is some 11, and so on. And I keep listing this out, right? So what I do is I create this list. F of 0, so f1, sorry, this is f1. So f1 of 0, f1 of 1, f1 of 2, and so on, right? So I just list out what the function value is at each point in time. Now, why is that good? Well, okay, if I can do this for one function, then maybe I can list out all such functions in such a way. So first, let's quantify. So let's say S is the set of all f's from n to n. So then S is a set like f1, f2, f3, dot, dot, dot. And the question asks us to determine if it's countable or not. So let me assume that S is countable, right? So this is an assumption. So I say assume S is countable, all right? So here, in some sense, S was listed out as a one-dimensional array. But because each of these functions can be listed out as a one-dimensional array themselves, I can list out S as, well, this is f1, which I'm going to list out as f1 of 0, f1 of 1, f1 of 2, f1 of some 10 to the 4, dot, 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 so on, f2 of 0, f2 of 1, f2 of 2, and so on. And I do this for every function in S, right? And let's see in a minute why this is good. So, okay, I have this listing. So this is how I've listed everything in S. Now, fundamentally, I'm able to list this because I have assumed that S is, in fact, a countable set, and so a listing exists. Well, okay, if I have such a listing, I'm going to follow an argument very similar to diagonalization, where I say, okay, let me make a new function, let me call it h, from n to n, such that h is defined as the function values along the diagonal, but with some changes. So I say, look, I say h of 0 is f1 of 0 plus 1. H of 1 is f2 of 1 plus 1. H of 2 is f3 of 2 plus 1, and so on. In general, h of k is f sub, let's just match the numbers, f sub k plus 1 of k, and then I add a 1. So what am I doing? I just picked off everything on the diagonal, and I added 1 to them, right? So now I've constructed this function h. Well, h goes from n to n. So then h belongs to S. If h belongs to S, and this listing was of every function in S, then at some point here, you have h itself, right? Listed this way. But then if h was listed this way, it would intersect the diagonal at that point here. So let's say h comes in some row number a, right? So then h is some f of a. Well, what is the diagonal element of h? So let's match some numbers. If h is f of a, the diagonal element is f sub a of a minus 1. Well, but then this must be h of a minus 1, right? Because it came on the diagonal. However, let's look at how I defined h of a minus 1. That was h of a minus 1 is f sub a of a minus 1 plus 1. And then we have a contradiction. So this must mean that such a listing cannot exist. And then if such a listing cannot exist, it follows that S is uncountable, because we are unable to list it. This proof had very similar flavors to Cantor's diagonalization proof. Okay, so that was part G. Now let's talk about part H. Before talking about part H, let's talk about, in general, So that was part G. Now to work on part H, we first have to establish a lemma where we talk about the set of all computer strings in the world. The set of all computer programs. So at this point, I make the claim any computer program can be represented in binary as a finite string, right? So the computer program itself might run infinitely and so on and so on. But if I were to write this out in code, I can convert the code to binary, and then it is just a sequence of ones and zeros. And in particular, one computer program is a finite such sequence. Okay, well, then all the computer programs must be a subset of all binary strings, right? Now, if I'm talking about all binary strings, these are all the strings of all lengths k, where one element is either 0 or 1. And I claim this is a countable set. Well, if I claim this is countable, I need to give you guys a listing. If I have to list it, the way I'm going to do it is I'll say, okay, well, 0, and then 1, and then 0, 1, and then 1, 0, and then 0, 0, and then 1, 1, and then 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and so on. So all length 3 strings. Then I list all length 4 strings. Then I list all length 5 strings. And all length 6 strings, and so on. And then I claim every binary string must come somewhere on this list. So okay, let's prove that. Let's say I have a binary string. It'll have some length k. Well, it'll show up in the kth section, maybe somewhere here. Over here, it might be one of these elements, but since this is itself finite, it's somewhere within this. And then every binary string appears in this listing. So then we see that the set of all binary strings is countable. But then if the set of all binary strings is countable, the set of all computer programs must be countable. Okay, so that was our lemma. Sorry, the lemma is that the set of all computer programs is countable. Okay, so that was a lemma. How do we use that for part H? Well, part H says computer programs that halt. Now, I don't know, given an arbitrary computer program, whether it halts or not. But all the computer programs that halt must be less than all the computer programs in the world. this set is strictly less than or maybe equal to all programs which halt. But now I just established with my lemma that this was countable, and then it follows that this must be countable. Okay, so that was part H. Now let's talk about part I. Part I talks about computer programs that always correctly tell if a program halts or not. We know by the halting problem that such a program cannot exist. So then the number of such programs is 0. But then 0 is a countable set because it's an empty set, and then the number of elements in this is 0, and so then this is countable, right? This set then is countable because 0 is countable. Okay, so that was part I. Let's talk about the last part, which talks about numbers that are the roots of non-zero polynomials with integer coefficients. But before that, we have to establish another lemma, something you've seen on the homework, which says that the countable union of countable sets is countable. Okay, what does this mean? Let's break it down. Let's say I have a bunch of sets A1, A2, A3, so on, where these indexes are all natural numbers, right? So the number of these guys is, if I put these all in a set, this cardinality is equal to that of the natural numbers. Because for every natural number, I have some a sub I. So over here, I have some a sub I, and that is uniquely mapped to some I over here. So we've seen such a construction on our homework. And now I claim that, let's say, each of the a sub i's is countable. Now I claim that if I do a union of all the a sub i's, and we say union over all the naturals, that this set is, let's call it A. So let's define it to be A. The claim is this is countable, right? Now, we won't go into the proof right here. But what this, okay, why is this true? Well, I won't go into the explicit proof here. You can read it up. But the idea is very similar to the way we prove that the set of all rationals is countable. So what you can do is you can make a mapping between A1 and n because it's countable. You can make a mapping between A2 and n because it's countable, right? Okay, so I won't go into the proof of this lemma here. You can take it as an exercise to prove. But let's see how we would use that for part J. So first, let me define the set P sub k as the set of polynomials of degree k, right? Which means P sub k is a polynomial of the form, so some p belonging to P sub k has P of x as some a sub k x to the k plus a sub k minus 1 x to the k minus 1, so on, plus a1x plus a0, right? Okay, well, this particular polynomial has k plus 1 coefficients which belong to the integers in integers, which means that the cardinality of P sub k must be less than or equal to the cardinality of the integers of k plus 1, because for every set of coefficients for a sub k, I can make a bunch of other integers here. And so really, p of x can be represented as a tuple of a sub k minus 1, a sub 1, a0. And this lives in the k plus 1 integers. And this, as we've shown earlier, has the same cardinality of that as the integers. Think about the proof where we talked about rationals. And then we showed that the two-dimensional space is equivalent in size to the one-dimensional space. And then this can be proved by induction that this is true. So then you have that each of the p sub k's is countable. And then finally, we can say that all polynomials with integer coefficients are just the union of all the p sub k's. And then by our lemma, this is countable.